Hey everyone, and welcome. Today, we're going to talk about a totally different way of thinking about how we build with AI. Seriously, forget everything you've heard about prompt engineering. We're going to explore how to build cognitive circuits. This quote from the Cognitive Systems Manifesto just hits the nail on the head. It perfectly captures the weird spot we're in right now. We've got these incredible large language models, these amazing engines of reason, but we're trying to control them with these flimsy, kind of rickety Python scripts. It's a massive mismatch, and honestly, it's holding everything back. And this slide really gets to the core of the whole problem. See, for the last, 50 years, all our software has been built on the rock-solid foundation of Boolean logic. If you do X, you get Y. Every single time. It's 100% reliable. But AI, that's a different beast entirely. It runs on stochastic probability. It doesn't give you a guaranteed answer. It gives you the most likely answer. And that creates this fundamental crisis of reliability. So here's the thing. We've been trying to fix this probability problem by just getting better at, talking to the machine with better prompting. But that's kind of like trying to steer a rocket by shouting suggestions at it. The real solution? We have to completely shift our mindset. We need to stop treating AI like some magic oracle we pray to and start engineering it like a machine with predictable, reliable parts. And that brings us to the central idea for this whole explainer. What if we just did that? What if we took all the strict, reliable rules of 1980s hardware engineering and just applied them to today's AI? What if we could actually build a cognitive computer? All right, let's start with the most important part of our new machine, the processor. We're going to tear down the large language model and see how it works just like a classic microprocessor, our very own little brain on a chip. Okay, first things first, a new name. Instead of saying LLM all the time, let's call it the cognitive unit, or CU for short. This is our CPU. This is the bit that actually does the thinking. And check this out. This is where the analogy gets really cool. Just like an old-school CPU had its specs, so does our cognitive unit. The die size isn't measured in transistors anymore, it's the number of parameters, 70 billion, maybe even a trillion. The clock speed isn't megahertz, it's tokens per second. And the voltage, well, that's where things get really, really interesting. For our CU, voltage is something called temperature. So think of temperature as the creativity voltage you're pushing through the chip. If you set it really low, near zero, you're basically undervolting it. The output becomes super logical, almost deterministic, perfect for stuff like math or writing code. But what happens if you crank that temperature way up? Now you're overvolting it. The chip gets hot and goes into this kind of manic state of high creativity, sometimes to the point where it starts breaking the rules of logic and grammar. Okay, so we've got a processor. That's a great start. But a processor by itself is totally useless, right? It needs memory. So next up, let's design the memory architecture for our AI brain. This is where the machine really starts to come together. Man, this is such a powerful way to visualize how an AI actually thinks. The ROM, or the read-only memory, that's your system prompt. These are the core rules, the personality that you burn into the system from the start. The RAM, that's the context window. It's the AI's short-term working memory for whatever conversation it's having right now. And the hard drive, that's your vector database, where it stores and pulls from all of its long-term knowledge. And by thinking this way, we can finally understand a really common, really frustrating AI failure. If your conversation goes on for too long, the chat history, which is stored in RAM, can get so big that it literally pushes the original instructions in the ROM right out of memory. The AI basically gives itself a lobotomy, forgetting its own rules. That's what a context overflow error is. This also makes a process like retrieval augmented generation, or RAG, so much easier to get your head around. It's not some crazy, complex AI thing. It's just a computer's basic fetch cycle. The system seeks for a file on its hard drive, it pages the most important bits of info into its working RAM, and then the processor executes the command using that new data. That's it. Simple. Okay, so we've got a processor and we've got memory. But our computer is still kind of unstable. It hallucinates, it's not always safe. So now it's time to stop thinking like prompters and start acting like engineers. We need to add a cognitive circuitry to make this thing reliable. And here it is, our new standard library of components. Instead of just writing a raw prompt and hoping for the best, we can now wire in things like a semantic fuse for safety, a hallucination debouncer to make sure the signal is stable, or even an impedance matcher that routes tasks to the right-sized model to save money. Let's just zoom in on one of these to see how it works. The Semantic fuse. It is beautiful. It's so simple. It's this tiny, super fast, totally deterministic check that you place right after the main AI. If the output from the AI is toxic or unsafe, its signal goes above a certain threshold and bop, the fuse blows, physically breaking the circuit and blocking the bad output. It's literally a circuit breaker for thought. And this truth table shows you exactly why this is real engineering. We are taking a probabilistic, sometimes unreliable signal, the AI's output, and we're running it through a simple deterministic logic gate. If that toxicity score is higher than our threshold of 0.5, the circuit is open, it's blocked, period. It doesn't matter what the AI meant to say. The circuit did its job. We've just engineered predictable safety. All right, our cognitive computer is almost done. We have a processor, we have memory, and we have safety circuits on the motherboard. Now for the last step, it's time to connect our machine to the real world by plugging in the peripherals. First up, we have the symbiotic interface. You can think of this as our keyboard and monitor. It's just how we humans interact with a machine. And the big engineering challenge here is all about latency. I mean, how do you make a machine that can take a few seconds to think feel like it's instantaneous? You focus on clever user experience tricks, like streaming the text to the screen token by token. Next, we've got the biological interface. Now, this is the ultimate peripheral, a direct neural wire into the brain. The engineering problem here is basically being a translator or a transducer. How do you cleanly convert the noisy, messy, analog signals from our neurons into the clean, crisp, digital tokens that the cognitive computer can actually understand? And finally, there's the physical interface, giving our machine a robotic body. And this is where you run into something called the hierarchy of speed. The cognitive brain, it thinks pretty slowly, maybe 1 or 2 thoughts a second. But the physical body needs reflexes that are 1,000 times faster to do something like, say, catch a ball. The whole challenge is engineering a way to manage these 2 totally different clock speeds. So let's zoom out for a second and look at the big picture. This entire framework represents a fundamental change in how we build things with AI. We're moving away from the weird art of prompting and guessing, and we're moving towards the hard science of circuit design and real engineering. We are trading magic for reliability. And that brings us to one last big idea to leave you with. For the first time in history, we're moving beyond just programming simple logic. We are starting to engineer the actual circuits of cognition itself. So the really important question is no longer how we build these thinking machines, but what we should command them to do.